recent developments, kind of a list of things. And for those of you who are maybe not as familiar and into kind of following the progress in FM, that should be useful to see what are new things. Okay, so jump right into it. So we've already heard we have the latest two new releases in the past year for 5.2 and 4.6. And so some of the features, so we had submesh and parse submesh added, previously. We discussed that last year a little bit. So now it's been extended to support Netlink and Ravi spaces. And this is illustrated in new examples 34 and 35. But the basic idea of this is, it allows you to do solving different physics on different subdomains and domains boundaries and transferring solutions between these kind of parent and child meshes. Okay, another new thing, we are continuing development of TMOP capabilities. So we've added some new metrics. These are so-called asymptotically balanced matrix. There is a whole set of those. And added also some auto-balancing of compound metrics. This allows you to, auto select some parameters that were previously had to be user specified. So this is kind of a nice utility. And there are some there are a few new tools, but I'm highlighting here the T-metric magnitude, which allows you to look at, okay, I have selected this metric, but what does it look like when I do my optimization? How does it evolve under optimization? Things like that. So as kind of a part of the TMOP development and the mesh optimization development, there is a new mini app where you can fit an existing mesh to specified surface. So the surface is specified via a level set function, which could be a discrete function. And I'll show an example of that, how this can be used for not topology, but shape optimization. Right, thank you. I'm forgetting the terms. So this is not gonna, I don't have a highlight slide for this, but this is also very cool. New DPG mini apps for various formulations, and they have some nice promise for solving indefinite Maxwell problems, because you get SPD system, which is quite nice and has a promise being a very, very efficient algorithm there, even though you may think, okay, DPG is maybe a bit more expensive, but overall, good solver is paying off here. So that's another. Okay, some other things. So these are kind of GPU related, a few of them. Improved debugging. So before we were using FM macros, those are still there, but for better debugging, we're now using Lambda templated functions, essentially. So the compiler has better line information when you're debugging, so you can step inside those functions to debug. That's kind of a nice, very, very easy, but nice extension that we added based on user feedback and recommendations, I think, mostly. HIP support, with the Sundaos integration and the PETSI integration. This is kind of an important missing link for us that we've addressed. And some of it is external collaborators, PETSI and Sundaos developers helped with that. So there is we added support for pyramids in non-conforming meshes. It's a nice addition, and we can import pyramids from Gmesh as well. So there is a mini app for fast normalization-based distance solver. That's another new addition, a distance mini app, and this is useful for in various contexts. So it's kind of a nice app that you can use for various things. Also, recently, the latest release, we had the KD3 capability. It allows you to find points in, arbitrary points in space on a mesh. And this is illustrated in this Nodal Transfer Mini app. I believe this is maybe in tools, or is it? I'm not sure what the location exactly is for this, but you can probably find it somewhere in the mini apps subdirectory in some of that. So there is a new development on the solver side for HDIF problems specifically, which is very, very nice addition, and that's being very, very important for some of our in-house applications. And this is illustrated in this HDIF linear solver. I'll talk about it a little bit more in detail after kind of the summary of these features. So we have updated MUMPS interface and new interface to MKL Paradiso. Okay, so some of this, I think, some of this you already heard. Simon mentioned it briefly. I just want to highlight some of the new NURBS improvements. So in meshing, we support free connectivity of NURBS patches. So CMesh, this is useful for CMeshes. I'm not sure exactly what that means, but I saw it. This is in the changelog, and I think we'll hear later today a little bit more about NURBS from actually the author of this, which was an external contributor. Very nice additional development. So there are some other features like allowing you to set attributes on patches and patch boundaries and do some interpolation for NURBS. And one thing that is kind of on the performance side with NURBS, we had capability in maybe some of the integrators, at least maybe 2 integrators for now, but this is kind of now has some framework for development for other integrators to do patch-based assembly for NURBS meshes, which is very nicely, very nice performance improvement, and it's it allows you to do also reduced integration there with some new kind of algorithms. This was developed by Dylan. So the new examples, or 4 new examples. So the first 2 are related to submesh, and you can see it's magnetostatics and time harmonic oscillator. You can view there is some documentation on those in the page that both Aaron and Zanio highlighted, nfm.org/examples. There are some nice pictures there and short explanation, or you could just read, the explanations at the beginning of these files. Example 36 is an interesting new method for obstacle problem that called proximal Galerkin. This was developed by Brendan. And the last one is topology optimization, simple topology optimization example in FM. And of course, there are many more that, I don't have the time really to go into very many details here. Okay, so this is maybe somewhat old slide, similar to what I presented last year, but kind of illustrates what submesh does. So we have all domains, are meshed together. So if you have a multi-domain problem, you mesh them together, and then you extract subdomains via attribute selection, for example. I think that's what's currently supported. And then but that allows you to keep the connection to the big mesh, and that allows you to transfer things. And it inherits from mesh, so you can do anything you can do with a mesh. And due to the conformity of the initial mesh, transferring is possible without any sort of interpolation between. So you're directly transferring those. So everything is exact in the discrete spaces. And so PowerMesh is also basically supports all that. inheriting the partitioning from ParMesh. And that could be a limitation, but something to think about and work on in the future. And there is the multi-domain mini app, which is, before we had the support for HDIF and HCR, which I mentioned on the previous slide. Okay, so this is also an outside. I'm just adding it here for kind of as an introduction, maybe to the next slide. So we've had this for some time now. It's lower the refined solvers, which are GPU enabled, and they are very suitable for GPUs and for high order methods. This was a kind of a big push for us to develop these in view of high order and the GPU focus that we had in the SEED Co-Design Center, but also, high order is very nicely fits on GPU. So if you use high order, as you saw in some of the performance plots, they basically low order does not give you the performance that you can get with quadratic cubic elements. And so using high order elements on GPU actually gives you better performance than linear. And there is some intuitive explanation to that. I'm not going to go into details. So these were applicable to H1. These are applicable to H1, HCR, HDIF problems. Hard elements, they can work on AMR meshes. So they're very, very simple to set up, as illustrated here, just like one line. And so these pie charts here illustrate kind of the transition from CPUs to GPUs, what it gives you in terms of kind of the different components in a solver. The setup here is kind of, on CPU is kind of cheap, but if you go to GPU, that becomes kind of a dominant cost. And these are things that architectural shifts, you can think of it, and I'm not sure if this can be avoided, but it is what it is, just the illustration of the effect of this architectural shift on the algorithm. So it's pretty much the same algorithm, just run on different architectures. Okay, so with that, so one gap that we wanted to improve on was the HDIF solver. So why was that a gap? Well, because we had this option for CPUs to do hybridized solver for HDIF, which is actually, in that context, was the best HDIF solver. So the LR does not translate quite easily when you're doing hybridization, which involves inverting local matrices. So this work by Tanya and Will Pasner, they developed a generalization of that kind of a settle point formulation with LR now included. And, it's not exactly hybridization, but it's kind of inspired by that. And you can see here the big improvements in performance. So this is the new solver on GPU and CPU are in green, so solid line and dashed line, and compared to some other timings, you can see that these are now the fastest solvers for a wide range of sizes, essentially. So very, very nice and practical. We know this is very important for some applications in the lab. And so this work is, I think, putting on par our GPU capability with the hybridization solvers that you can use with on CPU that were just developed for CPU mostly. Okay, so some let's see how I'm doing on time. You have to speed up, I think. So one important part for development is automatic differentiation in FN. And so this is a view of an optimization loop. So there is mesh environment and solvers. And during this optimization loop, you have some parameter that you want to optimize. So here in this representation, the parameter is really involved in this D here. So D is the, your bilinear form. What happens at quadrature points, right? That's where the physics happens. So a lot of the optimization parameters really work at this level. All these operators, they are still the same and fixed. So when you have this parameterization, you basically have this D, and now U, which is this product here of before. So this is in the linear case. So when this thing becomes nonlinear, typically you're still computing U with a formula like this, and you're computing rho in a formula like this, but then they interact in some nonlinear way here. So your operator now is, the nonlinearity is really in D. And if you differentiate this, basically the differentiation happens now at quadrature points. And that is that's what makes it very, very nicely and easy to do in some ways. Basically, when you're defining your operator, you can automatically differentiate, and if you use the enzyme to, that becomes really automatic by the compiler. It's a supported compiler level. So it can mix also different languages. So if your quadrature point evaluations involve function calls to like Fortran libraries, this with enzyme you can differentiate this as well. So and it does like one small ADs, as I mentioned, on quadrature points. Instead of trying to differentiate this whole box here, we are differentiating very, very much at the center, at the real quadrature points where most of the physics happens. And we only differentiating what's necessary, right? We are zooming in specifically to nonlinearity here. So this is, and as Tanya mentioned, this is focus of the MFM plus and DFM project, which is a collaboration with Enzyme. So stay tuned there. So how the mesh optimization. So this is a summary slide. Basically, what is TMOP? TMOP is a way to optimize meshes using minimization of forms like this. So you're basically integrating over each element. You have a metric mu, and then this T is your mapping between the desired shape of your element and the current shape of the element. So this mapping, you express it through the reference element and these kind of details, but basically this measures how much your current shape of the element differs from what you want it to be. And there are different metrics you can apply here, but it's a minimization problem, so it's kind of a framework. And these are some examples of the things we can do to adapt your mesh to features in your solution, for example, here. So these steep gradients, you can create a mesh like that, which is much more adapted to what the solution needs. And so, okay, sorry, I'm jumping. So this is the focus. So we've developed this GPU acceleration of this capability. So this was not available on GPU before. So with the new capability, we can, some benchmarks here. You can see speed ups to, multiple, 30, 40x compared to serial code. And so you can see also scaling pretty well here on different number of GPUs. I'll kind of glance here, but basically now our most, or if not everything in a TMOP capability now is GPU enabled. And this is also, it's an important for applications in Livermore. So this was a push to put things on GPUs. Okay, and so briefly mentioned this capability where you can align your mesh with a level set function. So you have a level set function, and you kind of it looks like this, and then you have this. You choose some elements, and the interface between elements. Now you align it with your level set to get this kind of a nicely aligned mesh with the level set given by this. So this is one of the TMOP related mini app that I mentioned in my list before, and it can be used, in 2D, 3D very nicely aligned here with kind of a mesh that it evolves, can evolve in time. So basically, this set is something that can be evolved in time and this is used in shape optimization, for example, but probably can be useful in other applications. And there is a mini app you can use to do that thing, at least as an illustration, and then you can embed it maybe in your application to put it inside an optimization loop or something like that. Okay, and I have a slide for highlight PyFM. This is the last thing I wanted to mention. So this is a slide from Sunichi. He's been one-man machine developing PyFM, right, for a long time. And so, yeah, all these releases, he's been doing this mostly by himself. So I think one of the major points he wanted to highlight here is the just-in-time compilation of coefficients, which is nice optimization, I think, for fast evaluation of things. And that has been a focus, and you can see how this can be done here in this snippet of Python code. And yeah, so we are getting some, he'll have some help from Livermore starting in January. And these are some of the things that there will be focus on documentation. You can see Python examples, update and refresh, basic Python methods, calls, and all kind of other interesting stuff. So Sunichi, I don't know if you're here. Maybe you can add something if I'm missing something that you want to highlight about JIT maybe or something else.
Leslie, this is nice. Thank you so much. This is perfect. Thank you.
All right, great.
Yeah, of course. We are looking, any input from the users, ideas, improvement, all welcome, and please put in the chat. Thank you.
Yeah, and so this is also on GitHub. It's a sub-project of the FM organization, right? So you have FM/PyFM. You can definitely post issues and comments there. Any feedback you can put there. This was already mentioned. I guess I have them repeated here. The seminar, the FM, the FM at LNL seminar, organized by FM people mostly. And the tutorial, which was already mentioned. So I'll stop here. And thank you. If you have any questions, I'll be happy to answer.
Okay, there were a bunch of questions for PyFM, GPU support, Windows.
PyFM and GPU support. Well, Sunichi, maybe. As I mentioned, he's the one-man machine there. Go ahead. Sorry.
I think yes, CUDA backend and all the other device-based backend, which is part of MFM, is wrapped in a 3 wrapper. So we don't have Python specific GPU capability on the PyMFM side. It is all we are just wrapping supporting the MFM's capability.
Right.
Mm-hmm. Okay, all right. But I think this will be something that we will be working on, right? In the SideHack application, you want to start using FM more and more in GPUs, correct? So there will be some developments there, right, Sunichi? That's the plan?
Yes. Yeah, that's a plan.
Okay.
I maybe also have a question.
Sure, go ahead.
So the GPU figures are very impressive, like 40 times speed ups, but these are obviously very expensive GPUs. But if you would use more consumer grade GPUs, would you expect similar speed ups, or is it maybe not even worth it to consider those?
Free lunch.
Yeah, so these are, as you said, these are more of a server type cards, right? So V100. I don't know what is actually in consumer cards, if they have full double precision support. I'm not. So some cards I know that are custom are purely single precision support, so we can't really use them at this point. FM is mostly, well, essentially double precision library.
Yes.
We are looking at extending it to support also flow. So at that point, probably using consumer cards could be viable if they don't have really double support even. I suspect that the performance on the particular GPU card will be somewhat lower, and it will depend really on the level of the GPU card. So if you have the highest end, like consumer cards, like the video, the highest end, like, I don't know, what is it, 4090 type RTX card, that might be on par with some of the results.
That's not cheap either.
It's not cheap either. Still might be a bit cheaper. Maybe it doesn't have necessarily like HBM memory, so these algorithms are memory bound, limited for the most part. So that will be another hit. The fact that these cards have GDDR. I don't know what's the specific ratio of the memory bandwidth, but that memory bandwidth is the kind of the main performance factor for these algorithms.
So
Okay,
Dennis,
yeah, thanks.
Dennis also posted on this about this on Slack, and let's keep the discussion there.